Hi, now we will discuss Compton effect. So previously we have discussed photoelectric effect. So when you recall photoelectric effect, so photoelectric effect is a proof. Okay, so Einstein proved that, or it can behave as a proof for particle nature of light. Okay, so light behaves as a particle is a big breakthrough. So particle nature of light is proved by photoelectric effect. So similarly, particle nature of light is again proved and supported by this Compton effect. Okay, so CE in the sense Compton effect. So what is the importance of Compton effect? It is also a kind of phenomenon or process which actually supports what Einstein said about light. What did Einstein said about light? He told that light will behave like a particle. Okay, so that light behaving as a particle is again supported by the effect called Compton effect. So now what is this Compton effect and what did he do? So very simple, he took a graphite. Okay, so he took some material which is made up of carbon. Okay, so the material which is made up of carbon that is easily available is graphite. Okay, so he took this graphite particle, okay, and he irradiated, I mean he passed X-rays onto it. Okay, so he passed what kind of rays? He passed X-rays which was having a lambda of lambda 1. Okay, so it was having a wavelength of lambda 1. Okay, so imagine there is a graphite particle and he passed X-rays onto it, and those X-rays were having wavelength of lambda 1. So that is the initial wavelength of the X-rays that he has passed. Okay, now what actually happened here is these X-rays got scattered. Okay, so these X-rays got scattered and they were having a new lambda, that is lambda 2. So there is a difference between the wavelength of initial X-rays and the wavelength of scattered X-rays. So these are our scattered X-rays. Okay, right? And actually what is the expected path? Okay, expected path is this. If light behaved as a wave, actually the expected path can be like this, but it scattered, and if light was a wave, it would have the outcome also, the scattered radiations also should have the same kind of wavelength. There shouldn't be too much, but here the scattered X-rays were having different kind of wavelength. Okay, so now the difference between the wavelength of initial X-rays and the scattered X-rays is what we mean by Compton effect. Okay, so what are the points that you can write is when X-rays, okay, so when X-rays were irradiated, that means exposed, irradiated on a graphite or on a piece of graphite, the X-rays get scattered. The X-rays gets scattered. Okay, right? Scattered, and the scattered X-rays, very very important, scattered X-rays, okay, were having a new wavelength, and usually the scattered X-rays wavelength was much higher than, okay, so this point is also very important, scattered X-rays wavelength, that means the lambda 2, if I consider the scattered X-rays wavelength as lambda 2, then our lambda 2 is much greater than much greater than lambda 1. That means initial X-rays. Initial, okay, X-rays. So guys, this difference, okay, very important, this difference of initial wavelength of X-rays and wavelength of scattered X-rays. Scattered X-rays is called as, Compton effect. So very simple guys, very simple. So what is that? Initial X-rays, they were having a kind of wavelength. Scattered X-rays, they have a different wavelength, and the wavelength of lambda 2, that is the wavelength of scattered X-rays, is much greater than wavelength of initial X-rays. So this difference is what we mean by Compton effect. Okay, so now wavelength is much longer in the sense what? The energy got decreased, isn't it? So this particular radiation was having a high energy, whereas this particular radiation has got a least energy. That means initially these radiations were having very high energy, but the energy of this radiation decreased. So what happened for that energy? High energy, but the radiation that came outside was having low energy. So what actually happened here was, so that energy is used up by the electron. So the electron gets ejected. So this is the ejected electron. Okay, so the energy gets converted into kinetic energy of ejected electron. Okay, and now this angle, the angle between the scattered radiation and the initial path, is actually called as theta. Okay, right? So based on this, he had given an equation. So the equation is very simple. Lambda 1 minus lambda 2, that is the difference in the radiation, is equal to h by m naught c 1 minus cos theta. Okay, so this is called Compton equation guys. So very important, Compton equation. So what is lambda 1 here? Lambda 1 is nothing but wavelength of initial X-rays. So you have to define all the terms here. Wavelength of initial X-rays. Okay, so what is lambda 2 here? Lambda 2 is nothing but wavelength of scattered X-rays. Okay, so h is a Planck's constant, its value is 6.6 into 10 power minus 34 joule second, and m is mass of an electron. So m is mass of electron, and whereas c is velocity of light. Guys. And what is theta here? Theta is that angle between, so it is the angle between scattered path of radiation and the initial path. Okay, so this is all about the Compton effect. Okay, so in an exam, what you can mention is, you can mention this experiment, this diagram, you draw it as it is and explain what he has done. Irradiated X-rays of having certain wavelength, that radiation helped for the electron to come out, but the radiation gets scattered radiation's wavelength is much longer than the wavelength of initial radiation. That means the initial radiation had got high energy, the scattered radiation have got low energy. So that energy that got mixed up here actually gets converted into kinetic energy of the ejected electron. Okay, so this difference in the wavelength between scattered X-rays and initial X-rays is what we call Compton effect. This difference can be obtained only if the radiation is interacting with a graphite, with this particular matter in the form of particle. Okay, only when the radiation interacts like a particle, okay, so then this kind of effect can be seen. So this is the greatest support for proving the particle nature of electromagnetic radiation. Okay, so actually what had happened, the radiation traveled in the form of photons. So it is these photons that had helped for an electron to come out, and some amount of photons have emitted, got scattered. Since the energy of these photon, some amount of energy of this photon has been used up to eject electron, the energy of emitted radiation or the scattered radiation decreased. Okay, so imagine you had 50 joules of energy for this proton. Out of 50 joules, maybe 20 joules have been used to do this process, to eject the electron from graphite. So remaining 30 joules would be the energy of the scattered radiation. So that is how the energy decreased. So this concept can be explained only when you consider the electromagnetic radiation is moved in the form of photons. Okay, so photon or quantum theory is the theory that supports that electromagnetic radiation behaves as particle. Okay, so in exam, mention this diagram, explain the experiment, explain the definition. Okay, so write the formula, explain the terms, so that becomes a perfect answer. So this is all about Compton effect. Now let us discuss about dual nature of matter. Dual nature of matter. So here dual nature in the sense what? Something having wave nature and something that also has particle nature. So that's what we mean by dual nature. So far what we have discussed was the dual nature of electromagnetic radiation. Okay, so the light has got wave nature, it has got particle nature also. Wave nature of light is proved by diffraction, interference, and the wave nature can be supported by which theories? Can be supported by Maxwell's electromagnetic theory. Okay, whereas the particle nature is proved by photoelectric effect, black body radiation, Compton effect. And particle nature is actually supported by and proved by what theory? Quantum theory of light. So quantum theory said light behaves as a particle, and photoelectric effect, Compton effect, black body radiation, all of them are proofs for saying light behaved as a particle. Whereas Maxwell's electromagnetic theory said the light behaves as wave, and that is also proved by the process called diffraction and interference. Similarly, just like the light had got dual character, so light can behave as a wave and it can also behave as a particle depending on the situations. Okay, similarly what the De-Broglie said was, so here we are going to discuss De-Broglie's hypothesis, okay, or De-Broglie's equation, I can say De-Broglie's hypothesis or De-Broglie's equation. So what did this person De-Broglie said was, just like electromagnetic radiation having a dual character, that is particle nature and wave nature, every matter means what? Matter is not radiation, right? Matter means I am a matter, pen is a matter, board is a matter, electron is a matter, proton is a matter, atom is a matter, right? Cupboard is a matter. So matter is anything under universe which has got a mass and occupies space, isn't it? So matter. So what he says is every matter, big or small, say human being is the biggest matter. Electron, smallest matter. Okay, matter means some particle, some object, some body. Okay, so just like light, what he said is even matter can have dual character. Even matter can sometimes behave as a wave and can sometimes behave as a particle. Very weird concept, isn't it? Right? So matter can sometimes behave as a wave and can sometimes behave as a particle. So you might get a doubt, okay, human body is also matter, How come we behave as a wave? Do we move in the form of a wave? No, right? Okay, say a ball is there. How come it is moving in the form of a wave, right? So one might get shocked by listening this, but this is true. This is actually proved, and I will tell that in few minutes. But the concept is this: what did De-Broglie said was, every matter has got two characters. Just like electromagnetic radiation, which had got wave nature as well as particle nature, every matter also has got two characters. Wave character is there, particle character is there. Okay, so this particular thing is actually proved with the help of mathematical equation. Okay, so what is De-Broglie's hypothesis? Matter also can behave, matter can behave both as a wave and also as particle. Okay, so this is what we call De-Broglie's hypothesis, and let us see what equation he derived and what equation he is giving as a proof for saying this. Okay, so he took fundamental equation E is equal to h nu. Okay, and you have studied another equation. Okay, say E is equal to h nu is the equation. Okay, so which is actually supporting, it is actually supporting wave nature of a particular matter or electromagnetic radiation. And there is another equation given by Einstein, that is E is equal to mc square. So this equation actually supports the particle nature of electromagnetic radiation or the particle nature of any matter. Okay, fine. So now he combined both equations. So E is equal to h nu, E is equal to mc. So E is same. So when this E is equal to this E, I can also write this h nu can be equal to mc square, isn't it? So h nu is equal to mc square, and we all know that your lambda is inversely proportional to frequency, and when you remove this proportionality sign, lambda is equal to c by nu we will write. Okay, nu is equal to c by lambda. So all these are very simple and basic derivations. You have learnt it in basic classes, isn't it? So for any wave, lambda is inversely proportional to frequency, and to remove a proportionality sign we introduced a constant c, and if I have to take a formula for nu, it is c by lambda. So in the place of nu, I will substitute c by lambda. So hc by lambda is equal to mc square. Okay, right? So now this whole thing I will move this side, lambda I am taking on the other side. So what do you get? hc by mc square is equal to lambda, and one c gets cancelled with one c here. Okay, so what is the formula you have got? Lambda is equal to h by mc. So what is c here? Velocity of light. In case of light, it is velocity of light, but in case of particle, I can write it as h by mv. Instead of c, I am writing v. V is a velocity of particle. Okay, right? So look at here, mv is nothing but momentum. Yes, so momentum is mv. What is momentum? Okay, momentum is a product of mass and velocity, momentum, isn't it? And this momentum is a nature of particle, okay, is a nature of particle, whereas lambda is the nature of wave. Wavelength is a nature of wave. Yes, wavelength is a character of wave, whereas momentum is the character of particle. So what is the formula you got? Lambda is equal to h by p. Okay, so lambda is equal to h by p. lambda is equal to h by p is called De-Broglie's equation. Is called De-Broglie's equation. Very important equation. So what is lambda here? Wavelength of particle. Wavelength. Lambda is wavelength. H is Planck's constant. Right? So H is your Planck's constant, whereas P is equal to momentum of particle. Momentum. Okay. So P is nothing but mv. Okay. Mass into velocity. Yes. So here P represents the particle nature, momentum represents the particle nature, whereas lambda represents the wave nature. Okay, so when you apply this equation to any particle, you can apply this equation to any particle, right? So, and from this equation one can clearly understand, see, in the equation your wavelength is inversely proportional to momentum. That means if you have more of wave nature, if this increases, this fellow will decrease, isn't it? So when you have more of wave nature, particle nature would be less. When you have more of particle nature, wave nature would be less. So this is very important. So what does lambda inversely proportional to momentum represent? So what does this represents? This represents when wave nature is more for any particle or for any matter. Okay, when wave nature is more, particle nature is less for any matter. Particle nature is less. Okay, so when something has more particle nature, then wave nature can be less. So that is what the meaning of this particular equation. Okay, so usually for microscopic particles, so this is very, very important. For microscopic particles, right, like electrons, protons, okay, neutrons and etc. For microscopic particles, wave nature is more, particle nature is less. So what does this mean? Wave nature is more, okay, particle nature is less. Particle nature is less. Okay, so very important. So electron, proton, neutron, they actually behave more like a wave. I repeat once again, this is very important. So your subatomic particles like electrons, protons, neutrons, they behave more like a wave, less like a particle. Whereas macroscopic particles, okay, so whereas macroscopic particles, okay, macroscopic particles in the sense what? Big particles like ball, okay, say this chalk piece it can be, or this pen it can be, or a human body it can be, okay, or a big mountain it can be, rock it can be, whatever. So macroscopic particles have less of wave nature, okay, and more of particle nature, right? This is what the concept, more of particle nature. Okay, so that's why we do have both characters, but wave nature is so less that it can be negligible. We completely behave as a particle. Okay, but the electron behaves more like a wave so that its particle nature can be neglected. Okay, so microscopic particles, microscopic matter have got more of wave nature, less of particle nature. They move more like a wave, whereas macroscopic particles like us, okay, behave more like a particle, less like a wave. But what he says is every matter has got dual character. It can behave both as a wave also as a particle, but depending on the size, some can have more of wave nature, usually the small particles like electrons, and some can have very less of wave nature that you can neglect, like human body, rock, cricket ball, football, etc. Okay, so that is all about De-Broglie's hypothesis. So what you have to write in the exam if it is asked, so you have to you have to derive this particular equation. So it's a very simple derivation. You just have to consider 3 basic formulas and equate it and simplify, go on simplifying, and you will get the major equation. Then define all the terms and then write the meaning, what actually the equation represents, and yes, so finally you mention this is more applicable to the microscopic particles. Okay, so De-Broglie's hypothesis, dual character, all this is more applicable for the microscopic particles. So that is all about De-Broglie's hypothesis. So the next very important concept in quantum mechanics is Heisenberg's uncertainty principle. So this Heisenberg's uncertainty principle, okay, is the fundamental basis for the discovery of Schrödinger's wave equation. Okay, so Heisenberg's uncertainty principle. So what does this principle says? So by this everybody have agreed that electron, so whatever electron is there, say for example you have a nucleus, around this electron will revolve. So everybody agreed that this electron will not actually move in a circular path. So this is a nucleus. So what we have learned so far is electron moving in a circular path. But what did De-Broglie said? Electron is not a particle, it has got more like a wave. Then it cannot move in a specified path. So it moves like a wave, like this. Right? So everybody agreed that electron is now behaving more like a wave. I repeat once again, electron behaves more like a wave. Okay, so now if you want to identify, okay, so if you want to identify position of electron, okay, or if you want to identify momentum of an electron, so momentum in simple term it means speed. So if you want to identify the speed of electron, or if you want to identify position of an electron at the same time, it is impossible, they said. Okay, so it is impossible to identify the actual position of an electron at a specific time where actually the electron is present around the atom. You cannot identify. And if you want to find out with what speed the electron is moving, you cannot identify. Okay, so both the quantities, I mean the position of electron and the momentum of an electron cannot be identified at the same time. This is what said by Heisenberg. Okay, so now I am going to write the definition of Heisenberg's uncertainty principle. It is impossible to find both position and momentum of microscopic particles right, like electrons, protons, etc. Okay, so usually for a microscopic particle, because it behaves more like a wave, at the time if you want to find out position as well as momentum, it is impossible. Okay, so what is the definition? It is impossible to find what? Position and momentum of microscopic particle simultaneously. So what do you mean by simultaneously? So the meaning of simultaneously is at a time. Okay, at the same time, if you want to find out both the properties of microscopic particles, it is impossible. Okay, so this is what said by Heisenberg. Okay, so actually he has done an experiment to find out the position and see what actually happened. So imagine an electron is moving like a wave and it is here, and from here it is moving. Okay, and it has come here. What is the expected path? So this is the expected path. So this is expected path of electron. Yes or no? So electron is here, so it is coming and it should go like this. So this is the expected path. Okay, so now you are very much interested to see where exactly the electron is there. So how do you see? You actually see with the microscope. Yes, so how does the microscope work? Microscope works on light. So what is a light? Light is made up of photons. Light is electromagnetic wave, right? So definitely you will focus some kind of photons. Yes, some radiations you will focus. So that much, say it's a very lightweight particle, isn't it? So this much radiation can be a disturbance for an electron. Instead of going like this, it would go like this. Okay, so this is the expected path, but this is what the deviated path. Okay, deviated path of electron you will find. So it is supposed to be here, but the moment you use microscopic light, the focused light onto the electron, these photons itself is a disturbance for an electron to deviate its path. So did you find position perfectly? No, right? You didn't find position perfectly, and that disturbs the speed of electron also. Okay, so you know, by different reasons, you know, you cannot find both position and momentum at a time. You can only find position correctly, or you can only find momentum correctly. If you try to find position correctly, you will get lot of error in momentum. If you try to find out momentum correctly, you will get lot of error in the position. Okay, so based on this, he has given a formula: delta x into delta p is greater than or equal to h by 4 pi. Okay, so whereas delta x is equal to error in position, okay, very important, and delta p is equal to error in momentum. Okay, see here. So this is the error in position, this is the error in momentum. How much the error can be? It can be greater than or equal to h by 4 pi amount. Okay, and now we all know momentum is nothing but mass into velocity. I will substitute here. So delta x into m is always a constant, it cannot vary. So m delta v is greater than or equal to h by 4p, and this m is a constant term. I will shift this side. So what is the final formula that we get? Delta x into delta v is greater than or equal to h by 4 pi m. Okay, so what is m here? Mass of an electron or mass of any microscopic particle. Okay, so if error in position is 0, then error in momentum can be infinity, isn't it? So if you have 0 error in finding position, I mean if you find position exactly, what does the meaning of this? If you find position correctly, okay, so you get lot of error in finding momentum. Okay, so if you want to find one correctly, when you are finding one property correctly, the other property will have lot of uncertainty, that means lot of error. Okay, similarly if delta p is equal to 0, then delta x is infinity, then delta x will be equal to infinity means too much. So delta p is 0 means what? If there is no error at all in finding momentum, that means you are finding momentum correctly. So in the process of finding momentum correctly, you are getting lot of error in finding position. That is what the meaning. Okay, but you need to know that this particular principle, this uncertainty, Heisenberg's uncertainty principle will work only for, it is only applicable for microscopic particles. It is applicable only for microscopic particles. Okay, so for microscopic particles, because they are more like a wave, you know, if you want to find out their location as well as if you want to find out their speed, both properties at a time, it's impossible to find the correct values. You might get some value, but you'll have lot of error in those values. So if you get correct value for momentum, you get very much high error in position. If you get correct value for position, when you don't have any error in the position, then you will have lot of error in the momentum. Okay, so in the process of finding one property perfectly, the other property will have lot of error. Okay, you will not get correct value for the other property. So both properties, if you try to find at a time, it's impossible, that too for a microscopic particles like electrons. So this is what about, this is all about Heisenberg's uncertainty principle.